is going to talk all about transformation. And we're going to do all kinds of different transformations. And when we see or hear the word transformations, what are we thinking of? What does it mean? Change, right? Something different. And you might even think of the word like Transformers or the movie Transformers, because you're changing from one vehicle into something else. And in this case, we are taking some type of geometric shape, whatever it is, and we are doing something to it, okay? In some cases, we're going to slide it left, right, up, or down. In some cases, we're going to make it bigger or smaller. Sometimes we're going to flip it over an X or Y axis. And so we're going to talk about changing it or transforming it in some shape or form. So today is going to be translations. Translations, the word that I use for translations is a slide. Okay, I think it makes more sense to say slide, and you'll hear me say the word slide a lot, because that's essentially what we're going to do. We're going to take whatever figure it is, and we're sliding it left, right, up, down, whatever direction. So on this first one, we can do it to any geometric figure. In this case, it's just a point P. I'm going to place point P at -4, 4. So we're going to go left 4, up 4. And we're going to label that as point P. And then what this does is this tells me what type of change we're doing to P. And so P, we're going to move P 2 units down and 2 units to the right. And what we're going to do is we're going to call that P prime. This symbol right here means change, right? So we've applied change to P, and so it's still P, but P in a different spot, right? And so that's why we use the same letter, P prime, just a symbol along with it. Okay, on this one here, they're telling us that P starts at -3, -2. So I'm going to do a different color here because we're starting over again. Left 3, down 2. Here, I'm going to call that one point P. And typically, we probably would want to use a different letter, but it's just a completely different problem. We're going to go 3 right and 3 up. And once again, we would call that P prime. Okay, so there's our 2 point P's and our 2 point P primes. And that's just what we call prime, is just the name of that second point. Here we're doing it with a point. Throughout the day today, we're going to do it to triangles. We'll do it to maybe a segment. We'll do it to all different types of geometric shapes and apply the changes to everything. Okay, today, and we won't see this a ton throughout the chapter, but we're going to talk about what we call the word vector. Okay, a vector is a quantity, that has both direction and magnitude or size. It is represented in the coordinate plane by an arrow drawing from one point to another. Okay, so when we do it, in this case here, you can kind of see PQ. It starts at P and ends at Q. The arrow shows the direction that we're moving. This here shows me how far we've moved to get from point P to point Q. So the initial point or starting point of this vector is P. P is where we're starting. The terminal point or ending point, a lot of times where you hear the word terminal might be like at an airport terminal. That's because that's where your flight ends at, right? I'm going to arrive at the airport terminal, and that's where that word is being used, or maybe where you've heard it before. Q is my ending point. We're going from P to Q, and we can see the arrow is showing the direction that I'm moving. If I started at Q and went to P, then my arrow would be pointing towards P. Okay, so that's how we tell which way we're going. The vector in this case is named PQ, and then here's a new symbol that we haven't seen before. It's kind of like a ray, but it doesn't have an arrow going top and bottom. It just has a kind of a half arrow on top. And so we read this as vector PQ. The horizontal component of PQ, horizontal means left or right. In this case, we went 5 to the right. Vertical component means up or down. In this case, we went up 3. If we went left, it would be a negative. If we went down, it would be a negative. But here, both of them were positive. Okay, and so then here's kind of the one thing that's a little bit different. The component form of PQ, we're going to use what kind of looks like less than and greater than symbols. But that's what we use for a vector. That's the symbols that we use for a vector. So it's not a parenthesis, okay? It's not an ordered pair. Ordered pair tells us this is where 0.53 is at. When I see these two symbols, that tells us the direction that we're moving from a point. We call that the component form. Okay? Questions on any of that so far? Okay, so if we look at this diagram, okay, which point is my starting point? Which point is my terminal or ending point? J is the starting point. So we're going from J to K. So that's how we decide what goes first and what goes second, based on where the arrow is at. We're going from J to K. Okay, so that's the name of this vector. And then when I put the component form in here, we got to count how far are we moving. We went 3 to the right. And 4 up. So our component form would be 3, 4. Okay. Just remember, once again, it is not an ordered pair, guys. Okay, it's not the ordered pair 3, 4. This is something totally different. That's why we don't use parentheses. That's why we're using a different symbol. Okay, the one on the right. We're starting at B, we're going to K. The arrow tells us the direction of this vector. So we start at B, we go to K, BK is our vector. Because we started at B, that tells me the direction that we are moving. So in this case, we're going to move left, 1, 2, 3, 4, 5. So that would be a negative. Because we move left, that would be a negative. And then to get to K, we got to go up 2. So negative 5, 2 would be our component. Okay, in this box, we've got some vocab that we're going to talk about here. First up, we already talked about this word at the beginning of the lesson. We're going to see this word a lot throughout the chapter because that's what this chapter is all about, transformations. A transformation is a function that moves or changes a figure in some way to a new figure that's called an image. The original figure happens before the image. So what prefix do we use when we say before? Pre, right? So the image that was before, or the figure that's before the image is the pre-image. So this is our starting figure. This is our ending figure, okay? Pre is before. The points on the pre-image are inputs for the transformation. The points on the image are the outputs. How do I get from one to the other? All of the movements should be the same throughout that transformation. whatever that is. And then we already talked about this. The ones that we're going to do today are what we call a translation. And I told you earlier that the word that I'm going to use a lot is a slide. Because we're going to take whatever figure it is and we're going to slide it in some direction. All right, so here we go. They're going to give us a figure. In this case, the vertices of triangle ABC. So we're going to plot triangle ABC. So we've got to be really good at plotting points here. So we're going to start off 0, 3. And I'm going to label each one of my points. 0, 3 is A. B is at 2, 4. C is at 1, 0. Because it makes a triangle, we're going to connect those 3 points together, and we're going to make our triangle. Logan, you getting all this? Okay, now this tells us what we're going to do. Okay, so this is the component form of the vector. So 5, negative 1. What does the 5 tell me? Right, 5. Okay, and then what's the negative 1 tell me? Goes down 1. So we're going to take all 5 points, or all 3 points, sorry, and move them right 5, down 1. Okay, I'm going to do this one in a different color just so we can kind of see what's going on here. It really doesn't matter which one you start with as long as you do it to all, and then it's just a matter of counting. We're going to label these A prime, B prime, C prime. And that would be our new figure. When I look at these two figures, what do we notice? What would be something you would say about these two figures? These two traits? They look the same, yeah. We haven't changed the size or the shape or anything of the figure. It's the exact same figure. We're just placing it in a new location is all we're doing. Okay? We've moved it whatever movement we want to do, and we've put it in a new spot. Okay. So once again, this one we're using some different letters, but it's still the same idea. When we give you a graph, we'll try to give you a graph that you can fit all the points on that graph, but we're plotting it all on the same piece of graph paper. 2, 2 would be L. 5, 3 would be M. 9, 1 would be N. So we have triangle LMN. Hey, and I always think it's easiest to count. In this case here, the first number tells us how far left or right we're going to go. So in this case, since it's negative, we're going to go left 2, and we're going to go up 6. If they ever ask us for L prime, M prime, and N prime, and writing them as ordered pairs, that could be the thing that they might ask us to do. Okay, and so what we would do is we would take each of these ordered pairs and we would subtract 2 from the x. So 2 minus 2 would be 0, and we're going to add 6 to the y. So that would be 0, 8. If I did M prime, 5 minus 2 would be 3. 3 plus 6 would be 9. And then for n, 9 minus 2 would be 7. 1 plus 6 would be 7. Those would be my 3 new order pairs. So you could just take those 3 order pairs and plot them, or you could still just count whatever direction you want to go. Now, if I wanted to come up with the order pairs, I could also plot them first and then just identify where the order pairs are at. So there's a couple different routes that you can go here. So L, we're going to go left 2, up 6, and make our new point. And we're going to call that L prime. M prime. And N prime. And the reason I tell you about the two figures looking the same is if I do something wrong when plotting these points and the two figures don't look quite right, if they don't look the same, what did I do wrong, right? So always make sure, at least for right now, that these two figures look exactly the same. They're the same figure. They're both triangles. They're the same size. Everything about them is the same. Okay, this one we're kind of going the opposite direction. They give us the two figures right from the start. We have to identify a translation rule for those two figures. Okay? Now what you got to be careful of here is identify what is happening or what's going on. Okay? And so when we write a translation rule, if I want to go from P to P, okay, first thing, now, we're starting with P, right? P is my original point, P prime is my new point. So prime is always the ending point. So if I want to go from P to P prime, we're going to move left 1, 2, 3, 4, and we're going to go up 1. So we are going left 4, up 1. Okay, if we write a vector rule for that, there's a couple of different ways that this could be written. The vector component would be negative 4, 1. That tells us how far we moved. Okay, if I wanted to write a rule as ordered pairs to show what's happening here, I'm going to take all ordered pairs, x, y, and we're going to add 4. Oh, sorry. In this case, we're going from the prime back to the original, so that's why we're going to add 4 and subtract 1. Okay. If I wrote the vector rule for this one, it would be 4, negative 1. Okay. So this is a translation rule. We call this a translation rule. This is a vector component form. They're both doing the same thing, just a little bit different way of representing it. Okay. It's kind of like sometimes you have decimals and sometimes you have fractions, even though they're the same thing. Those two are the same thing, just a little bit different form that we write it in. Okay, one's an ordered pair, one's vector form. But be really careful about what you're starting with and what you're going to. Here they kind of switched it up on us a little bit. We started with the prime notation and we went back to the original notation. So be careful what the question's asking. Okay, on this one here, write a rule for the translation of PQR to P prime, Q prime, R prime. So we're going to start here, and we're going to go to here. Now, does it matter which point I start with, P, Q, or R? No, because they all should be the same, right? If I go from P to P prime, Q to Q prime, or R to R prime, all of those should be the same rule, okay? You don't necessarily have to do all three of them either. I mean, if you want to check it, you definitely can, but all three of them should have the same rule. So it doesn't matter what one I choose to use here. So I'm just going to start with P. When we go from P to P prime, just because we want to do X first, we're going to go left 1, 2, 3 until we get even with it. And then we're going to go down 1, 2, 3, 4. So we go left 3, down 4. If you need to, you could even, draw that in on your graph and say we're going left 3 and down 4. Okay, translation rule. When it says a rule for the translation, usually we're talking about the ordered pair unless it says the vector component form. So in this case, we're going to say x minus 3, y minus 4. If I wrote the vector component form, it would look like that. Okay. Once again, those two mean the same thing, just a little bit different way of writing it. And that would be our movement. Hey, now all that's happening on the second one here is we're going from the red to the blue graph, or triangle. So guess what happens with my numbers? If I was going to go from P prime to P, what direction would I move first? Right. So I'm going to move right 1, 2, 3. And then I'm going to move up 1, 2, 3, 4. So what happened with my numbers? The sign just changed, right? Instead of moving left 3, down 4, now we're moving right 3, up 4. Same numbers, just the opposite sign. So when I write a rule here, I would say x plus 3, y plus 4, or the vector, bless you, would be 3, 4. Okay. I probably won't do both of these because these are both essentially the same thing. We haven't done a quadrilateral yet, so I'm going to do the quad on top. We've already kind of done some triangles. In this case, it says to graph. And on this one, what I'm going to do here is I'm going to do A, B, C, and D. We're going to plot those first. Oops. Four, 6, and 4, 2. Hey. So there's my original quadrilateral. Okay, in some cases it's going to ask you to identify the ordered pairs. So I'm going to show you how to come up with the ordered pairs. We kind of talked about this already. So I need A prime, B prime, C prime, and D prime. Okay, I'm going to put these in red just to do a different color here. Okay, we're moving right 3 and down 1. And there's a couple different ways that you could do this, okay? you could apply those numbers to what we have here. So if I did -1 plus 3, that would put me at 2. And if I do 2 minus 1, I get 1. So we're going to go over 2, up 1. Okay, -1, 5. I'm going to go right 3. And I'm going to go down 1. And then we're going to go to C. We're going to go right 3, down 1. And then finally, we're going to go right 3, down 1. Be careful that when we make this new figure, the new one is going to be A prime, B prime, C prime, and D prime. Hey, now could I just count and tell what this order pair is here as well? I really don't care how you do it. You can either do the actual math where you do addition, subtraction, or you can count and tell me where that order pair ends up. But we want to identify the location of A prime, B prime, C prime, and D prime in some shape or form. Okay? Everybody good there? I don't feel like there's any need to do a triangle. You guys feel pretty good about that all so far? It would be the same thing, it would just be a triangle. All right. This one here. We got a lot of, like I said, we got a lot of notes today. Translation postulate. Translation is what we call rigid motion. Okay, a rigid motion is a transformation that preserves length and angle measure. Another name for rigid motion is an isometry. A rigid motion maps lines to lines, rays to rays, segments to segments, triangles to triangles. We could do anything, right? It doesn't matter what the geometric figure is. We could map this figure onto this figure using rigid motion. And so here's the thing. As you look at these two figures right here, DEF and then D prime, E prime, F prime, what's going to be true about that? We've already talked about how those two figures are exactly the same size, right? But not only are they the exact same size, this segment is the same length as this segment. And that's the same for all three segments. The segment length is the same for all three. The angle measure. See how this marking and this marking are the same? Whatever this angle is, okay? All three angle measures will stay the same as well. Okay? If I had 4 sides, then all 4 angle measures would stay the same. So when it's a rigid motion, when we simply just slide it, the figure has not been changed at all. Everything is preserved in that movement, in that change, in that slide. Okay, and that's what this is saying here. All 3 segments are the same, all 3 angles are the same. Nothing happens, nothing changes. They're all preserved. Okay, on this one here, what we're going to do, when we apply 2 or more transformations, so now we're going to look at applying multiple transformations, we're going to result it into what we call a composition. We're going to kind of combine them into one total movement based on the 2 combined movements. Hey, Mr. Elegant. Hey, looking good. Yeah, you bet. These are both really smart, right? Went to the same place. Okay. A composition theorem is a composition of 2 or more rigid motions to make a new rigid motion. Okay. This theorem is important because it states no matter how many, I could do 5 different rigid motions, and what would be true about those figures? if I applied 5 different movements or 5 different slides, and I started with a triangle here and I did 5 different changes to that triangle, what would be true about my triangle at the very end? It'd be the exact same triangle, right? It doesn't matter how many movements or changes I do to that, then it's still going to be the same triangle. That's what a rigid motion is saying. The triangle is preserved all the way throughout all the different movements that are happening. All right, so here's what we're going to do. We've done it with triangles, we've done it with a quadrilateral. Now we're doing it with a segment. So we got segment RS. We're going to plot the points -8, 5. And -6, 8. There's R, there's S. We're going to label it R and S. Okay, first thing we're going to do is we're going to move it 5 to the right and 2 down. So if I move it 5 to the right, -8 plus 5 would be -3. And 2 down would be +3. Okay, and then we're going to do it to S. If I move it 5 to the right, -6 plus 5 would be -1. 8 minus 2 would be 6. There would be R prime, S prime. Okay, now here's the trick. And I never did connect these two together, but I did make a segment. Okay? When I make my new change, I'm applying it to my new figure. I'm not going back to the original. So I've changed it. Now I'm taking the new one and I'm changing it again. Okay? So now, and that's where writing these ordered pairs is going to come into play and probably be a little bit helpful. Now here's the part that's going to be a little bit different is on this one, we're going to call it R double prime. That double marking means we've done it twice, right? It's kind of like we did that with segment markings or angle markings. When we do 2 markings, that means that's the second one, right? So this is the second slide or the second change. So if I was at -3, 3, and I subtract 4 from the x value, what'd I get, Adrian? Because you're talking to Bryson, you don't even know what the question was, probably. Huh? Okay, we're going from the new figure. Okay, so that would be -7. And then my y value was at 3, and we're going down 2, so we get 1. So -7, 1. Okay, and we're going to label that one as R double prime. Okay, for S double prime, we're going to take our new point, -1, 6. We're going to go left 4, down 2. So -1 minus 4 would be -5, and 6 minus 2 would be 4. So -5, 4. And we're going to label that one S double prime. Connect those two together, and those are our 3 different figures. If I look at all 3 of those figures, notice how all 3 of those segments are the same length, same figure. All of them are the same. Okay? Yeah. All right. I'm gonna skip this one up here because essentially it's the same thing we just did. Okay? Not much difference here. It's still a segment. We're applying 2 different changes to it. How could you use the translation rule to determine location, coordinate, point T without graphing? Okay, so what I will tell you on this one here, okay, if I wanted to get from T to T prime, we've already talked about this, okay, you could put it onto if I wanted to get from one to the next, okay, so first of all, if I take this point here and I subtract 2 and then I subtract 4 more to get to the very last figure, how far have I moved total? If I move left 2 and then left 4 more, how much have I moved total? 6, right? 6 to the left. So this would be x minus 6. Okay, and then the y values. Okay, if I look at my y values, if I go 3 down, but then I go 5 back up, how far have I moved total?
8.
So if I'm here and I go down 3,
2.
I've only actually moved 2, right? So my composition movement would be y plus 2. My total movement, okay? Because I moved down, and then I moved back up.
I'll pay attention.
Okay, so what we're saying here is add or subtract the values to get the total change, the total movement. Okay, last one for today. There's 2 of these, but we're just going to do one of them. Okay. We have floor tiles that we're going to move around. You move 1 tile right and 3 tiles down. Okay, so what we're going to say here is that our original tile is XY. Okay, we don't necessarily know the location of it, so we're just going to call it XY, right? If I move it 1 to the right and 3 down, how would I express that as movement? Okay, but we can't just write 1, negative 3. X plus 1, yep, because we have to say what are we doing to the x value, so x plus 1 and y minus 3. Okay, and that's why we don't just want to say 1, negative 3, because 1, negative 3 is a point, right? If I said ordered pair 1, negative 3, that is a point. We are saying what am I doing to the x, what am I doing to the y? So this tells me what is happening or applying or changing to the x and y value, okay? Then we're going to do a second change. So from where I'm at right here, now we're going to move 2 left and 1 up. Okay, and so then to finish this, the composition is the combination, or putting this all together to find out what's the total movement that took place to get from my original location to where I'm at right now. I moved right 1, and then I moved left 2. So how much have I moved total? Left or right? How much? If I go right 1, and then I go left 2, which direction? If I'm on a number line and I move right 1, and then I move back 2 to the left, negative 1. Yep. So this would be x minus 1. I could also get that by taking 1 minus 2, right? which is -1. My total movement is -1 at the end. Okay, if I move 3 down, but then I move back up 1, I've only moved down 2. Total. That's what we call our composition transformation rule. We're going to combine the 2 individual movements into one big movement to make our change. Okay, so that is it was a long set of notes, and that's what I